Let's have a look at examples of heat equation. In a sense, physical situations that can be modeled by heat equation. So the most obvious examples are any temperature distribution. For example, you can consider a rod having fixed temperatures at the two endpoints. How you know the initial distribution of temperature, how does that evolve over time? And at some point, it's going to be just a straight line from the two different temperatures. Or you can think of a heating pan that we can look at it like a cylinder, a full cylinder. So a three-dimensional heat equation. You can fix the temperature at the bottom, that is heating it up, and fixing the temperature at around the cylinder and on top of the cylinder. And you want to see how the temperature disperses from the bottom around it. And what you can again imagine is that after infinite time, it's going to be a sort of the temperature would disperse up on the cylinder in such a way that in every direction you're going, you see a linear decrease in temperature. But before you get to that point, the temperature is changing over time. A more complicated example you can think of is molten iron cooling in a mold. So you got the iron at a given temperature, you pour it in a mold, you assume it doesn't cool off while pouring it, so it arrives everywhere in the mold at the same temperature, and then you want to see how it cools down. A more complicated model would also take into consideration that the iron would move while cooling, but a default modelization would just check the temperature of the iron. You can start by assuming that the mold has a constant temperature and it's not going to be affected by the iron that has been poured in it, or you can make a more complicated model that allows the mold itself to heat up due to the iron. And in that case, you have two heat equations that are coupled at boundary, because you have the ion that is losing heat and transferring this heat to the mold, and the mold that is gaining heat. And over time, both of them are going to be cooling off. Not literally a heat equation, but something that, in my opinion, is quite interesting to look in this context is the Schrödinger equation. So the Schrödinger equation has this form. So it has the derivative over time minus the delta of a function psi, and then a non-homogeneous term of order 0 depends on psi is the product between psi and a vector field v. And if you write it like this is exactly the heat equation with some forcing term that is multiplied by psi itself. But this is not the Schrödinger equation, actually, because you have one extra term that multiplies your time derivative. That is the imaginary number times the Planck's constant. You interpret this as saying that the Schrödinger equation works with imaginary time. So time is usually considered to be strictly real, but not when you're dealing with quantum mechanics. Schrödinger equation is fairly complicated to solve in anything that is not a absolutely trivial situation, partially because of this imaginary time and partially because of that multiplication between your potential V and your psi, that is the solution you're looking for.